Hi there, Miss Barber here. This lesson is titled Apportionment Methods. To apportion means to allot or allocate a countable number of objects or people in an appropriate and ideally fair way. A significant social choice issue involves apportionment. That is, the apportion of representatives to the U.S. House of Representatives. In this lesson, we will examine some of the methods explored in the attempt to solve this apportionment problem. Before examining different methods of apportionment, we will define two important terms illustrated in the following scenarios. Scenario 1. Mom has 50 caramels and 5 kids and wants to give each child a fair amount of candy according to the amount of chores they do in a week. The table below shows the minutes worked for the first week of summer vacation. In a fair world, how many pieces of caramel should each child receive? The table shows that Anna worked 150 minutes, Bob 78, Clark 173, Doug 204, and Emma worked a whopping 295 minutes. With 50 caramels and 900 total minutes, we can compute 900 divided by 50, which gives us 18. This tells us 18 minutes of work for one caramel. Now we have a reasonable way to reward each child with the caramels. For example, since Anna worked 150 minutes, divide that by 18, and that results in 8 1/3 pieces of caramel. Bob worked 78, so we divide that by 18 as well, and that's equal to 4 1/3 pieces of caramel. Clark did 173 minutes of chores. Divide that by 18, and that's equal to 9 11/18 pieces of caramel. Doug did 204 minutes of chores. Divide that by 18, and he has earned 11 1/3 pieces of caramel. And finally, with Emma working a whopping 295 minutes, divide that by 18, and she has earned 16 7/8 pieces of caramel. The question is, how does Mom accurately divide a piece of caramel into any of the above fractional parts? That's probably not possible, so we need to look at maybe something called apportionment. Scenario 2. The Republic of Happystan is having an election for their legislature. According to Happistan's constitution, 25 legislators will represent the 4 different territories. The following table gives the population of each territory. In a fair world, how many representatives should each territory get? The table shows the territory of Athens' population is 375, of Berlin's as 225, Cleveland 175, and Denver is 150. If you sum up the population for the 4 different territories, we get the population of the entire Republic of Happystan, which is 925. Now, before we proceed with finding how many representatives, we need to define some new terms. The first one is called the standard divisor. The standard divisor is the total population divided by the number of items to be apportioned. Here, the total population is 925. The number of items to be apportioned are the legislative seats. That's 25. The next term is the standard quota. The standard quota is the population divided by the standard divisor. So A, find the standard divisor for Happystan. The standard divisor is computed as the total population divided by the number of items apportioned. The total population is 925. We divide by the number of legislators, which is 25, and the quotient is 37. That is our standard divisor. Part B, find the standard quota of each territory. To find the standard quota, we need the standard divisor, which we computed in the previous part as 37. Have your calculator handy. We have a whole lot of arithmetic to do. To find the standard quota, you take the population, so for Athens that's 375, and then divide it by the standard divisor of 37. And let's round this to about 2 decimal places, so the standard quota is 10.14. Again, have your calculator handy for Berlin. You do 225, divide that by 37. That's approximately 6.08. Let's do this for Cleveland. 175 divided by 37, got 4.73, and for Denver, 150 divided by 37, that quotient, 4.05, is the standard quota for Denver. The sum of the standard quotas should be 25, which is the total number of legislative seats. The sum of the standard quotas must be the total number of items allocated. The legislative seats, or at least the people serving them, are indivisible. We could select just the integer portions. So, we're looking at this table. The standard quotas are marked. And if we select just the integer portion, then Athens would get 10. Berlin, 6. Notice I'm not rounding at all, just going to the integer portions. Cleveland, 4. And Denver, 4. The issue, though, is when you add those up, 24. The total seats then turns out to be 24 instead of 25. You still have one unassigned seat. Here's the tricky question. What is the right and fair way to decide which territory gets that one seat? We have several options to consider, and to answer that question, we study the 230 plus years old discussion among the U.S. citizenry about apportionment. We'll define some terms and then look at some apportionment methods. The next definition is called the lower quota. The lower quota is the integer portion of the standard quota. In other words, the standard quota rounded down to the nearest whole number. That's regardless of what the decimal numbers are following it. And the upper quota is the standard quota rounded up to the nearest whole number. Now let's look at one of our first options called Hamilton's method. In Hamilton's method, every state gets at least its lower quota. As many states as possible get their upper quota, with the one with the highest residue, which is the fractional part, having the first priority. The one with the second highest residue, second priority, and so on. So the steps are: calculate the group standard quota, initially assign each group their lower quota, and then give the surplus items one at a time to the groups with the largest decimal parts in their standard quotas. Do this until all surplus items are allocated. Example 1. The math department has to determine how many teaching fellows, denoted TFs, will be allotted to teach 5 of their first year math courses. The department has 30 TFs and 750 total students. To do this, we begin by finding the standard divisor. The standard divisor is computed by taking the total population and dividing it by the number of items apportioned. In this scenario, you have 750 students and 30 TAs. So that's equal to 25. The standard divisor is 25. Part B. The table gives the number of student enrollment in each math course. Use the standard divisor to find the standard quota for each course. Have your calculator handy. Just key in the numbers and get the output. For the standard quota of the 1100 math class, it's 188 divided by the standard divisor 25, conventionally rounded to 2 decimal places, that's 7.52. For 1180, it's the student enrollment of 142 divided by the standard divisor of 25, that's 5.68. For 1580, take the 138 students, divide it by the standard divisor of 25. You see about 5.52 on your calculator. And for 1680, with the enrollment of 218, divide it also by the standard divisor of 25. That's 8.72. And for 1710, with 64 students currently enrolled, divide that by 25, and that's 2.56. Part C. Determine how many TFs will teach each math course and which courses have the upper quota. Hamilton's method, we find the standard quotas first. That's done. Now we assign the lower quotas. The lower quotas are just the integer portion and we ignore the decimals. So 1100 is 7, 1180 is 5, 1580 is also 5, 1680 is 8, and 1710 is 2. Let's add those up. I got 27 TAs. That means we still have 3 unassigned TAs. According to Hamilton's rule, we start with the class that has the highest residual, that's the decimal portion, and I see the highest one as 1680. So for 1680, we give it 1, and now we're down to 2 unassigned TAs. The next highest decimal portion I see is the 0.68, which is for the 1180, and so for the 1180, that class gets another TA, and now we still have 1 unassigned TA, and the largest residual, or the decimal portion, goes to 1710 with 0.56. So those courses get 1 more TA. Let's add them up. 1100 gets 7, 1180, 6, 1580, 5, 1680, 9, and 1710 gets 3. The sum of those 5 numbers is 30. And the next question is, which courses have the upper quota? The upper quota, see 1180, we see 1680, and also 1710. Those are the classes that got the unassigned TA. Hamilton's method was one approach. We've got different ones. Notice that with Hamilton's method, we relied on rounding the end results of the standard quota. Another approach is to adjust the divisor so that the rounded standard quotas add up to exactly the number of items apportioned. Let's define some terms. First is a modified divisor. A modified divisor is a divisor that is altered to yield a preferred result, and so a modified quota is a quota obtained with a modified divisor. We use a modified divisor and modified quota for the next 3 approaches. Our next option is Jefferson's method. In Jefferson's method, you choose a modified divisor so that the modified quotas, when rounded down to the nearest whole number, will add to the number of items to be apportioned. Steps are: find a suitable modified divisor. Next step, use the modified divisor to find each state's modified quota. And finally, apportion to each state its modified lower quota. Here's an interesting historical note. Congress approved Hamilton's method in 1790. President Washington vetoed it. Jefferson proposed a method, and it was adopted. Congress resurrected Hamilton's method again in 1850, and it was used until 1900. What method is used for apportionment today? Option 3 is called Adams' method. With Adams' method, you choose a modified divisor so that the modified quotas, when rounded up to the nearest whole number, will add to the number of items to be apportioned. The steps are: find a suitable modified divisor D. Step 2, use that modified divisor to find each state's modified quota. Step 3, apportion to each state its modified upper quota. And finally, we have option 4 called Webster's method. With Webster's method, again, you choose a modified divisor so that the modified quotas, when rounded to the nearest whole number, will add to the number of items to be apportioned. Step 1, find a suitable modified divisor. Step 2, use that modified divisor to find each state's modified quota. Step 3, apportion to each state its modified quota conventionally. 0.5 and above, you round up. Below that, you round down. Example: 4 investors pool their money to buy 200 shares of a stock. The amount each person contributes is shown in the following table. Apportion the stock according to the method used. The table shows Anson pitched in $15,020, Barton $3,320, Carlton $19,600, Dyson $10,060. Together, they're going to buy $48,000 worth of stock. I'm going to skip part A, which is Hamilton's method. It is worked out for you in its entirety in your notes. And from that portion of your notes, let's recall that the standard divisor is the total population, $48,000, divided by the number of items to be split up. That's 200 shares of stock. So we have a standard divisor of 240. Part B says use Jefferson's method. For Jefferson's method, we find a suitable modified divisor and then add the lower quotas. With Jefferson's, the modified divisor will be less than the standard divisor. This is primarily just guessing. So step 1 is find a suitable modified divisor. This can take a few attempts. My first modified divisor attempt, I'll do it with 239. So what that means is take, for example, Anson's contribution of $15,020 and divide by 239 instead of the 240 that we did for Hamilton's method. And that quotient is 62.845. On your calculator, you should quickly check for Barton. Do 3,320 divided by 239. And check for Carlton, 19,600. Divide that by 239. And let's do Dyson ourselves. So we'll do $10,060 and divide that by a modified divisor of 239. And that gave 4209. The next line of the table says the modified quota, and so the modified lower quota, is just the integer portion. So for Anson, 62. For Barton, 13. For Carlton, 82. And for Dyson, 42. Key these into your calculator. 62 plus 13 plus 82 plus 42. I got 199. And that's not good because we need 200. So we'll indicate that we tried 239 and that didn't work. So let's try this again with a modified divisor of 238. We want the final result to be a little bit bigger, so we'll make the divisor a little bit smaller. In your calculator, let's do 3,320, that's for Barton, and divide that by 238. I got 13.95 in your calculator. Let's do this for Carlton. He pitched in 19,600, a modified divisor of 239, and I got 82.35. You should check on your calculator right now. Do 15,020, divide that by 238, see if you get 6311. Similarly for Dyson, 10,060, divide it by 238, and see if you get the 4227. Now we pick the lower quota. Again, that's just the integer portion. So with 238, the lower quota for Anson is 63. For Barton, it's 13. For Carlton, 82. And for Dyson, 42. Add those four numbers together. It should be 200. Since we got to 200, we have a final apportionment. According to Jefferson's method, Anson should get 63 shares, Barton 13, Carlton 82, and Dyson 42. Part C, Adams method. Let's remember that the standard divisor we computed as 240. That's our starting point. In Adams, we find a suitable modified divisor and then add the upper quotas. With Adams, the modified divisor will be more than the standard divisor. This will take a few attempts. So let's first try with 241. That's 1 unit more. In your calculator, let's find Barton's. 3,320 and divide by 241. I got 13.78. With your calculator, quickly check for Anson. Do 15,020 divided by 241. For Carlton, 19,600 divided by 241. And similarly for Dyson's contribution of $10,060. Your value should match the 62.32, the 81.33, and the 41.74. Now this time we take the upper quota, so we round up regardless of what the decimal says. Modified upper quota for Anson is 63. The modified upper quota for Barton is 14. For Carlton, 82. And for Dyson, 42. Add those numbers up. Use your calculator. 63 plus 14 plus 82 plus 42. I got 201. And that's too many. We only have 200 shares. So what we learned is that 241 didn't work. We need less shares, so we need our divisor to get a little bit larger. And we'll try it with 242. For Anson, take the $15,020 that he pitched in and divide it by 242. I get 62.07. Let's do this for Dyson. $10,060 divided by the modified divisor of 242, and Dyson's modified quota is 41.57. We pick the upper quota for each of those, and so 62 becomes 63, 13 becomes 14, 80 becomes 81, 41 becomes 42. Add those four numbers together. The result's 200. Everything is divvied up, so our final apportionment would be that Anson gets 63, Barton 14, Carlton 81, and Dyson 42. Part D, Webster's. With Jefferson's, we know to pick a modified divisor that's a little bit less than the standard divisor of 240. With Adams, we know to pick a modified divisor that's a little bit more than the standard divisor of 240. With Webster's, it depends entirely upon how things work out. The first thing that I tried was the standard divisor. The values are on your chart. For Anson, the modified quota, 62.58, Barton, 13.83, Carlton, 81.67, Dyson, 41.92. Then we round conventionally. The 0.58 for Anson rounds the 62 up to 63. The 0.83 for Barton rounds the 13 up to 14. The 0.67 for Carlton rounds up the 81 to 82. Same thing happens for Dyson. The residual is 0.92. We round it up. The result is one too many. That tells us we need to make the divisor a little bit bigger. And so, after trying a few of them, I found that 240.4 works. On your calculator for Anson, take his contribution of 15,020 and divide that by 240.4. The output, 62.48. Barton's is already computed for us. Let's do Carlton's. 19,600. Divide that by 240.4. Use your calculator. And that quotient, 81.53. Now we're going to round conventionally. 62.4, that stays at 62. 13.8 rounds up to 14. 81.5 rounds up to 82. And 41.8 rounds up to 42. The sum of those four apportionments is 200. So the final apportionment, according to Webster's method, 62 for Anson, 14 for Barton, 82 for Carleton, and 42 for Dyson. You may have noticed that the shares are pretty much the same, but I'd like for us to compare them by apportionment methods. By Hamilton's, Anson had 62. By Jefferson's, Anson had 63. By Adams, 63. By Webster's, 62. All of these are within one of each other. Barton, the lowest contributor, was 14 with Hamilton, went down with Jefferson, and 14 with both Adams and Webster's. Carleton, the biggest contributor, 82 with Hamilton's, 82 with Jefferson, 81 with Adams, 82 with Webster's, and Dyson, regardless, stayed the same. We observe that compared to Hamilton's, with Jefferson's method, the smallest contributor loses a share and the largest competitor gains a share. With Adams' method, the smallest contributor gains a share and the largest contributor loses a share. Here's something for you to think about. At the time when Jefferson's method and Adams' method were proposed by Jefferson and Adams respectively, did Jefferson represent a large state or a smaller state? And I asked that same question for Adams. And then go back and take note that with Jefferson, the smaller loses, larger gains, and with Adams, the smaller gains and the larger loses. What we need to see in apportionment methods is the quota rule. The quota rule states a group's apportionment should be either its upper quota or its lower quota. An apportion method that guarantees this will always occur is said to satisfy the quota rule.